Welcome to Searching for the Question Live. I am very glad to have all of you here with us. We are streaming live on YouTube, Facebook, and Twitter. And you're welcome to subscribe to the YouTube channel and click the bell icon so that you can be alerted when we are live again the next time. The guests that we have had over the course of over 60 episodes of Searching for the Question Live have come from all over the world in many different disciplines and technologies, and representing ideas of all kinds. And some of them I have known just for a few months or actually met for the first time online. Some of them I've known for longer. Today's guest is someone whom I've known for over 30 years because Tommaso and I went to university together and studied physics at the University of Padua. Physics for me has always been a great scientific, intellectual love, and certainly when I decided that I would not become a physicist was an important decision. At the time, I knew I didn't want to be a cog in a machine of the ever larger experiments that were being designed and then implemented on one hand. And on the other hand, I didn't feel I would be smart enough or diligent enough to be able to contribute to theoretical breakthroughs. And I have to say, in certain ways, nobody else has been, because over the course of the past 20, 30, 40 years, theoretical physics has had really important challenges that it in many ways failed to overcome. So the field of higher energy physics is fascinating for many, many reasons. It is probing simultaneously the smallest components of the universe and the farthest reaches via energies that are unavailable in our world, but are still available either in stars or around black holes, or in the glimpses that we collect in cosmological events of quasars or Big Bang and so on. So certainly it is a world full of fascination. So I'm very happy to have Tommaso Dorigo here with us.
Hello, everybody. Welcome.
Thank you for joining, and
thank you for having me.
We are live. So if there are going to be questions that are relevant and interesting, I will be very happy to pull them in, and we can answer them or comment on whatever our audience is going to share with us. Now, as I am wont to do, I prepared just a couple of things here. This is Bergamo, where I am, and I prepared Venice, even though I think right now you are in Padua, right?
Yeah, I'm in Padova, and I've moved from Venice to Padova 2 years ago because it's just so much simpler to commute from my home. It's 7 minutes by feet, and from Venice it was more than 1 hour. And as you know, Venice can be not so easy to live in. It's
absolutely. It is a beautiful city, but very impractical.
Right.
It is great if you are a tourist, but if you are a resident, you were in Dorsoduro, am I right? Do I remember correctly?
No, I lived in Santa Croce, which is a quartiere, let's call it in the Italian name, close to actually a train station when you get in, or by car if you have a car.
Okay.
Yeah, that makes it for an easier commute, but it's still over an hour to get to my office, and it's just better this way. Let's say.
So this is Padua, which has some nice things as well.
Yeah, the city.
The paintings from what's his name that are here. The
That's
fresco.
Quella degli Scrovegni with yeah. There's a painting with the Halley comet by Giotto there.
Giotto, there you go.
Speculated to be by Giotto, but of the Halley comet, but actually things match pretty well. Anyways, I shouldn't be commenting about that because you might be surprised, but I've never been inside.
Oh, yeah. Well, you should.
Yeah, I will
recommend you would, because it's great. It's really very nice. So here it is.
Right, that's the Halley comet.
Okay, very good. And I think I missed the Halley because when it came by a few years ago,
maybe possibly in 1986. Yeah,
it wasn't very bright and it wasn't very spectacular, but Hale-Bopp was fantastic. I know
I remember
one of your passions is astronomy and astrophotography as well.
Yeah, so, more astronomy. I'm a visual astronomer. I'm an avid galaxy hunter with my telescope.
So when Hale-Bopp came 13 years ago, it says, it was really spectacular on the sky. And I remember with my son Cosimo, I would hold him in my arms and we would go outside on the terrace of our house to watch the sky before he went to sleep. And every day there would be the comet, this incredible transient image in the sky. He doesn't remember, but that is what we would do. Okay, so when we went to university together, did you know that you would stay in the profession?
Tough question. I was fascinated by physics, as you mentioned, you also were, and I did imagine that I could have liked to continue doing research, but of course that's anybody's guess where you end up, right? And for me, the turning point was seeing an ad for a summer student program where I could, for 3 months, go to the Fermilab laboratory near Chicago, and I started there doing particle physics, and I've never ceased since. So that was a turning point for me. I mean, sometimes the easiest, I tend to say that the easiest decisions in life are those that you don't have to make, because they jump at you, right? So
well, one of the most dramatic proofs of this is how life expectation among males in East Germany declined after unification, because they were unprepared to make the gazillion decisions that the state, formerly very authoritarian, wouldn't make for them anymore. And they just couldn't cope with the weight and the cognitive necessity of all those decisions.
It's stressful, yeah. So
Emiliano from Twitter says that Spritz is coming from Padua, but I am not sure. Do you believe Spritz is Venetian or from Padua?
I don't even want to enter this kind of discussion because, first of all, I don't drink Spritz. I prefer Prosecco or beer.
Okay.
Second, because this kind of arguing will only, you don't usually settle disputes this way. You have to do some research.
So Wikipedia talks about Spritz Veneziano. I don't know if there is also a Spritz from Padua in Wikipedia.
Wikipedia is written by humans.
That's right.
Unfortunately.
So You didn't move to the US, though, even though it was an important part of your decision of becoming a physicist professionally. You never ended up, stably there.
No, I did. I did make a move after my PhD. I got hired by Harvard as a postdoctoral fellow, and I moved there with my family, in fact. And the fact is that in 2002, I had to, 2001, in fact, I had to decide, that was a decision I had to take, whether to accept another position or to go back to Italy, where there was another possibility for me. And I took the decision to go back to Italy because it was easier also for my family, but I don't regret it. Maybe I did less of a fast career here than I could have in the US, but I'm very happy of what I'm doing and what I've been doing. So no problem about that.
Do you still have any teaching duties too, or you don't have any classes anymore?
I am in a very comfortable position because as an INFN first researcher, I have no teaching duties. I do research. I can spend my time thinking. I can stay at home and in bed thinking for all the time, and that still counts. But I don't do that. Actually, I am mostly coding or writing things, grant proposals.
Well, you can, as long as after thinking you write an article that gets a scientific paper that gets 10,000 citations.
Yeah, that's a graph of all my publications. There's almost 1,600 of them. But I do also some teaching, in fact, because I like to. And in fact, I am spending lots of time in dissemination and outreach. And I teach a course in physics, particle physics, at the Master in Statistical Sciences here in Padova, because I think that statisticians can help basic research in fundamental physics. In fact, I've been the chair of the statistics committee of my experiment CMS at the Large Hadron Collider, at 3,000 strong collaboration. And there is a committee of people knowledgeable in statistics, which I chaired for 4 years. And there we have to steer the data analysis to avoid ad hocery and do good science. And by doing that, for many years, I've realized that the PhD students that work for us and do the hard-working core group that do the data analysis and squeeze out the information of the proton-proton collisions we create, these people have a very strong background in physics. Of course, they are PhD students in physics for the most part, but most of their time is spent in statistical procedures, machine learning applications, and data quality certification, data handling, computer science. So I think that we can bring in, if we can bring in students that know a little bit of physics through me, but have a background in statistics, we win. So that's an experiment I'm doing.
And you are absolutely not alone in the sense that many disciplines realize how important data science is becoming for them, and how little the native practitioners are able to take advantage of the new tools that are more and more essential to derive actionable conclusions from the deluge of data available. Last week, we had a couple of PhDs in molecular biology who created a platform for data analysis in genomics and proteomics and many other kinds of omics. And they designed it with ease of use in mind, so that the skills of IT practitioners and data scientists could be leveraged with a maximum efficiency, and at the same time, those who are the specialists in their case of virology or cancer studies or any other kinds of applications of that field wouldn't need to become specialists also of AI.
Yeah, that's a common problem, that there is a bridge to gap, because there are all these fantastic new tools in machine learning. There's artificial intelligence everywhere, but it's application specific. And the applications that you need to develop in fields of science, such as the one you mentioned, or epidemiology or particle physics, are special enough that it takes effort to develop the right interfaces. And so a computer scientist may be interested, but not so much, in doing a lot of work to make his tools available to us particle physicists. And so what we as particle physicists have been doing for a long time, was sort of using things that were off the shelf, like boosted decision tree, gradient boosting, neural networks, and the most efficient new ways of doing classifications or regression tasks. But we were never able to actually get to the cutting edge of it, for several reasons, also connected to a sort of inertia of the field, and people that are a little bit older and don't get it, that it's very important that we go in that direction. So it's a challenge, and it's actually my focus of research at present. To do exactly
half jokingly, I am looking forward when the next generation, or the generation after the next, of transformers is going to be applied to physics. These are pretty large neural networks with currently hundreds of billions of parameters that traditionally are applied for natural language generation. So you seed them with a certain paragraph of text, and they generate the next few paragraphs. And of course, they have no idea what they are doing, but the results are mind-blowing.
Maybe they do.
Well, sooner or later, those of us who don't believe there is a magical component in human consciousness will have no problem claiming that they do. But no, they are not there yet. At least when you turn off the computer in the evening, they don't scream to stop you from killing them. So in that sense, they are still far from being self-conscious. But I wonder how this kind of interaction between AI and human specialist is going to evolve in the future. Because of course, for me, it is very, very natural to believe that every specialty is going to have a cognitive co-pilot with the human specialist. And just like we use telescopes or particle accelerators, and nobody feels that it's cheating, because you should see the stars with your naked eye, or the particles with your finger, plucking them out of the vacuum. Well, similarly, nobody will say that it is cheating to supplement your cognitive ability with the reasoning that AI is going to be able to provide you.
Yeah, we are definitely living in interesting times, and I agree with you. It's not cheating. It's something that is going to happen because you cannot stop this kind of progress and development.
You wrote a book about your experiences. How was the need and the possibility of formulating your thoughts for a wider audience of non-specialists? Because this is not a book for physicists only. There's
not a single formula, because I was taught that every formula you add to a physics book decreases the number of readers by a factor of 2. So it goes very quickly. But the book was not meant for a large audience. It was a book that arose as a need to tell the story of how scientific collaborations, large ones, this one is the CDF collaboration that it's centered on 600 people at Fermilab, and they are working as a single man in trying to further our knowledge in particle physics. But of course, humans have egos, and large egos, when they are forced to walk past each other in narrow corridors, exert friction on one another. And so there are rules on how to publish and not to publish data. If you see an anomalous signal in your data, you would like to go out and scream that you have found something new, but you have to obey those rules. And so the dynamics, the internal sociology of these large groups of scientists is incredibly entertaining to
and if I'm not mistaken, you have had some clashes because you felt it was totally appropriate to write something in your fairly popular blog.
Yeah, yeah.
And the director of CERN happened.
Oh yeah, no, that's only one of the episodes. Yes, I mean, I was able to piss off practically everybody with my blog, but it's been 15 years, so I had a lot of time to do that. But yes, because collaborations act as a single man, as we say, but inside there are many things that happen, and then you pop up a result. But before you do, things are internal, they are secretive. There's some level of confidentiality. And so if you want to do outreach and explain what we are doing to laypersons, sometimes you want to also explain things a little bit more. And so you may leak out, not purposely, but sometimes your collaborators will get upset at you because they will say that you should not have said this, or you should have said these other things. Why didn't you quote me? Why didn't you cite me? Why did you cite me? All sorts of possible things have happened in so many years of blogging, and I was on the verge of being kicked out of this large collaboration. It couldn't have happened, but they tried to. Because I had, in their opinion, done something they didn't like. I mean, it's very the various ways in which I've got in trouble with my blog would be the subject of.
And I don't want to reopen old wounds.
No, let's not go there. But you know what? I will say one thing.
This video is from 2008 when I met Sergio Bertolucci, and without naming you, but he was very proud of open communication policies, blah, blah, blah. So I asked him, so, okay, what about blogging? And his answer was a politician's answer. So
yeah, it's hard. But things are changing. And I was always saying that I was investing a sizable fraction of my time to do science outreach. And I think I did a good thing. 10 million people have visited my blog in these years. And
wow.
And I think that my career was hampered by this in some way, because your colleagues don't like what you're doing. They think this puts a megaphone in your. I mean, newscaster. I mean, people like Dennis Overby will call me on the phone to know about the new result rather than calling the spokesperson. So this doesn't fit well. Okay. So it doesn't sit well with the way collaborations work. So there is enmity and the jealousy and stuff like that. But also, but my point is that at the end of all of this, what I've started doing is applying self-censorship, which is very bad, because you sort of say, I would like to write this, I think it's interesting. And then you say, oh, but I really can't write that, or I will get that person mad. And then you revise things. And you lose a little bit of interest in blogging, really, by this. Sorry, but this is...
No, absolutely. Also, your colleagues don't realize that the skills that you have in outreach and clear communication that non-specialists appreciate are fundamental for them as well, because sometimes, not often, but it is the lack of those skills that lead to projects not getting the funding that they would deserve.
Also, yeah,
because they are not sold well. You know, when the superconducting super collider was denied funding, it is rumored that one of the reasons is because the congressional committee meeting where the funding should have been secured, the scientist was not able to answer whether they will find God. And I don't know.
You should have said, "I assure you, we will find God." No problem.
Absolutely. Of course, just give me the money. I will deliver you God on a silver plate.
No, because a rubbish question deserves a rubbish answer.
Of course.
But things are changing. Things are changing because there is some level of recognition that is starting to appear for people who do intense outreach endeavors and then take on these things. And this, you can see this in the fact that if you ask for a grant to the European community, for instance, you will have to explain how you are going to do science dissemination. And if you do,
and also because physics is not being done. True, not true.
What?
No, I am just giving you the opportunity to explain that LHC has been successful.
Okay, so if this is the question, the LHC is an incredible endeavor that started at the end of the 80s. It took over 20 years to build. It was done with one purpose. We knew it was the only machine that could give us an answer to the question on the existence of the Higgs boson, a particle that was concocted by a physicist, a few physicists actually, theoretical physicists in the 60s, to explain some inconsistency in the theory that was being developed during those years. And it took an incredible amount of technology and new advances and betting that new technologies would become available later on after you started designing the thing. And we did it, and it was an incredible joint effort of more than 10,000 people, and in the end, this particle was discovered, and it has the properties that were predicted. And so it's an incredible human achievement. And it's also a bit disappointing because now people say, oh, but physics is boring because you say that there was this particle and you find this particle, and where's the fun? Where's the excitement? Where is all these supersymmetric particles that some of your fellow theorists were swearing would be pouring at us at the moment we would turn on the darn machine? Well, those particles haven't appeared yet. They might still be there. I don't believe it, but they might. I famously bet $1,000 that we would find the Higgs boson, but no more new physics with the LHC, and I won it. And
were you paid?
What?
Were you paid?
Yes, I was paid. Yeah, I went to Paris for a weekend with that money. So, I mean, I think it was important to build the LHC, and we are still squeezing it for new information, and we will continue to do so for the next 20 years, 15 years, as the recent update of the European strategy for particle physics has deemed important. It's crucial that we extract as much information as we can from that glorious machine, which is being, in fact, upgraded for the task to high luminosity, which means getting more data. But that's not the end of the story.
And you have a chart for this, which is this one. So here, past is on the top. We are here in 2020.
Yep, it's confusing, huh?
Well, I'm just explaining it, and the future is in the bottom. And in the horizontal axis, we have energy expressed in electron volts, kilo, mega, giga, tera, and peta. And so LHC is around here. It is getting towards 1 tera electron volt of energy. Now,
yeah, you shouldn't read it literally, because those arrows are sort of indicative of the range of mass, because you know that mass and energy are interchangeable, and in fact we use energy to produce mass. So that the range of 1, 2, 3 TeV is more or less the range of energy of mass of particles we could discover. Yeah, sorry to interrupt.
no, of course, of course. And so you say this machine is going to go for at least another 10 years or more, and then sometimes
Possibly.
towards 2040, or between 2040 and 2050, we will turn on another machine. So tell us about the new machine.
So this is just a schematic to show that every new major accelerator has discovered new things, and we should. There is a big discussion that says that there are people that say there are no physics theories that reasons, deep theory reasons to let us imagine that by constructing a machine that is more powerful than the LHC, we will discover new physics. But the truth of the matter is that discoveries are technology driven. When we have a potential to build a new thing and explore new ground, we do it, and usually we gain knowledge by doing so. So this project, so there has been a 2-year-long process whereby the most knowledgeable of our seniors in particle physics have thought deep and long about what to do, how to pursue, to further our research on fundamental physics. And this is the European strategy up to date of particle physics. And they have come up with a series of recommendations. And one of them is not to build a new machine or to invest, give us the money and we will invest and we will be happy for 20, 30 more years. No, what they did was, what they said was, we should seriously understand the feasibility technologically and budgetarily of building a new collider of a larger scale that can probe matter at a much shorter distance scale with higher energy. And they have drawn a very clear path forward that was more or less what was done at the end of the 80s when the LHC was conceived. And as you know, you have mentioned the SSC, which was this other machine that aborted, that was to be constructed in Texas, was going to be even larger and more powerful than the LHC, but was killed by a budget cut. Now, we have to face the fact that what we do is very expensive science, and also by the fact that we cannot promise that we will discover God or produce new dividends and fallbacks to society. It is true that by building these huge, incredible machines, we are straining the technological limits, and this pays large commercial applications, and that we then all end up benefiting of. But yes, this is a possibility. The path forwards has not been undertaken yet, but we have a definite direction to investigate where to go.
So how do you describe the interaction between theoretical physics and experimental physics? Because you mentioned the interaction between technology and physics, of how LHC was conceived before what could make it possible was available, and so the entire field of applied sciences in superconductors and magnets, and even obviously data processing, supercomputers, collaboration software, all kinds of tools were developed. And let's not forget that the World Wide Web was born at CERN before the LHC, but
flower on the Yeah, that was something that was developed at CERN and then was given.
So the necessity of this kind of interaction is very clear. However, today, as I mentioned at the beginning, we are at a point in theoretical physics that it is not clear where we need to go.
Yeah.
What was the 20, 30 years ago, 40 years ago, the expectation was that there would be a certain class of theories, and we would pick out of that very large class of theories what actually corresponds to our universe, and we would be able to make it simple, unify gravity with quantum mechanics, and have a deeper understanding of the universe and of the phenomena with predictions that could be verified experimentally. And that didn't happen.
So there is this interplay of theoretical predictions and experimental verification or disproving theories. And we have been doing this in parallel very well. And in fact, this has brought us forward very quickly to understand we have an incredible amount of understanding of matter at the smallest distance scales. In fact, we have this theory, the standard model, which predicts with incredible precision everything that will happen when we do particle collision or release energy in a small scale.
Quantum electrodynamics is the scientific theory that has been experimentally proven to the highest precision among anything we have. And if we built bridges with that kind of precision, they would never fall. And if we built skyscrapers with that kind of ability, they would reach the moon. So absolutely hats off to both quantum electrodynamics and to the experiments that worked out the numbers.
Those were Feynman and Schwinger in 1957. They developed this theory and got the Nobel Prize for that. But of course, then you had to measure the electromagnetic moment and verify these predictions so precisely. So that's the interplay that I was discussing. Right now, the interplay is sort of blocked, and we are in this sort of a crisis, as you were mentioning, right? And crisis is a good word. A moment of crisis is a very creative moment. If you know the word in Greek, it has this meaning where you can actually look at what you have on the table and try to sort out. It's not like somebody told you, go for the Higgs boson, and you go for it and you get it. Right now, we are in a more fluid situation. But there is one thing, this incredibly precise model that we have concocted and understood and allows us to compute things is inconsistent, and in the sense that it has some paradoxes within. And that has been used to claim that there must be new physics that explains those paradoxes. Now, physicists have been, many theoretical physicists have been basing predictions that we would find new physics with the LHC because of this apparent inconsistency. But now that we haven't found these potential supersymmetric theories or whatnot that would explain this problem, which is called the naturalness problem of the Higgs boson mass, now we are a little bit on our own, right? So we have to think forward and say, we have the technology now to go forward, and possibly we will discover something new. Or maybe we might be unlucky and not discover anything new, but we will still learn a huge amount of things that we still have to experiment about, what is called not new physics at the high energy scale, but still things we still don't understand very well. And we will do this by leveraging things that, as you were saying, we don't exactly know how to do right now. I should mention that I am right now writing a proposal for a grant that will allow me, if I get funded, to do something that is now possible with the computing science tools that have recently been developed, in particular what is called differentiable programming. Because I was mentioning even before that machine learning, we use it as physicists, but we have to tailor it to our needs. And so we are not on the bleeding edge of it. So instead, in principle, there is now the possibility to perform end-to-end optimization of physics measurements or even detector design. So I want to do that. And to do that, you need to create a very complex architecture that is capable of considering together with the intrinsic stochastic nature, the randomness of the quantum world, to produce a differentiable model of that we can then navigate to find the maxima of our utility functions. That is the best possible measurement given a certain amount of money and a certain amount of time. Once I have considered all possible systematic uncertainties and stuff like that. This is a very complex thing, but now there are the possibilities to do it, and I want to prove that it is doable. So this is one way forward that will require the development of things that are not yet even possible. And there is another thing. If we construct now a plan to build a future circular collider, like something that will come into operation in 20, 30 years from now, and we do it by designing detectors that it will not be us who will use, but it will be artificial intelligence systems 20 or 30 years down the line, because we know that it's going to happen, because we know that already the reconstruction of this complex collision event that we do in our detectors is demanded to specialized algorithms which do not have artificial intelligence in them yet. But in 20 years, it will be for sure. So we have to think at design optimization with that in mind and extrapolate to the future capabilities that these systems will have. This is the challenge, I think.
That is really wonderful, and it is a concrete example of what I mentioned at the beginning of a cognitive co-pilot, where it is not just analyzing the data coming out of the machine, but it is sitting on your side, designing the machine then that it will have to work with. You also mentioned the optimization parameters, including the money available, the resources available, or the time, etc. And that has been a bane of physics for a long time, because hedge funds would suck away talent, running after money, optimizing trading algorithms instead of applying everything that they could to the new science. So this is certainly very interesting. We have another couple of provocative questions from Emiliano.
I love provocative questions.
Well, he's asking if LHC is a time machine, and how many chances do we have to be able to travel to the past?
These people have been looking too much into at that serial on TV on Netflix, Dark, where people travel back and forth through the future.
Okay.
Let me answer these questions. So the LHC is not a time machine. What we do, though, is to zoom into the smallest distance scales by colliding particles together, by creating very energetic collisions. It's like we illuminate matter so that we look into it like with a very powerful microscope. Time doesn't get in the equation. It is one of the four coordinates of space-time, of course, and like any other space coordinate. But it's not like you can travel backward and forward with time. Particles can be thought of doing that, but it's just one way of seeing antimatter.
Well,
no, we not to travel fast.
The near maximal velocities in vacuum, close to the speed of light, that the particles are accelerated towards, make it so from their subjective reference frame,
true, yeah,
time
sure.
is almost at a standstill, which is the reason that they last enough to actually be able to collide before they disappear into swarms of other particles.
Yeah.
So the relativistic effects of time dilation are a fundamental component for the machine to work. What is definitely the case is that even though time slows down close to zero, and the photon, which the LHC doesn't use, it uses other kinds of particles, always traveling at the speed of light, has time at zero. So forgive me the poetic expression, but a photon lives at every time, all the time, because by traveling at the speed of light, for the photon, there is no difference in slices of time between each other.
That's right.
Even though it gets close to zero for the particles, it never gets to less than zero. And the reason, Emiliano, this is so important, and Esther is complimenting Emiliano for the question, is that we believe today that if we were able to move energy or particles or action or anything back in time, we would destroy causality, the sequence of causes and effects that are representing today a fundamental structure of the universe as we see it. And physicists are ready to give up on everything: space, time, energy. You can matter. You can destroy every concept you want, but they are not ready to give up on causality. So if we ever
beer.
and beer, causality and beer. If we ever are able to design loops in time, what I think is that the result will be disappointing, in the sense that the place we end up is going to be just so radically different that it won't matter. So, for example, I have no reason to exclude, except everything physics is about, that in 10 to the 100 years, let's say, when protons decay and this universe starts to be unable to create new structures, there could be seeds of a future universe, either being born from the evaporation of black holes, freeing up naked singularities, or from some other effect, and that there could be some interaction in a loop-like fashion between subsequent generations of universes that are being born like this and our birth. So,
yeah, I have an even different view from you. We are just speaking freely, but I think it's interesting to conceive the possibility of this multiverse. Now, I don't buy string theory. That would be a different discussion. But in principle, you can think that our universe is a bubble that is expanding, but there are infinite other bubbles expanding at different times, and in principle, everything can happen in these other bubbles. They are causally disconnected from ours, of course. But this also gives you an idea that we could replicate, our universe could cease to exist and then replicate itself ad infinitum. So we could, in the end, be condemned to live an infinite number of times and make the same mistakes an infinite number of times. But yeah, that's just. But I think there was another question that was bounced off us, right?
He remarked on whether it is bending time, and yes, if you wish, exactly because we are talking about a four-dimensional space-time continuum. As you apply very strong magnetic forces accelerating the particles, you are simultaneously bending space and time from their point of view. So that is absolutely correct. But while space is such that they go around in a circle, time is not. Let me ask us. Yes, go ahead.
There was one other thing to add. One of the things that this European strategy up to date brought forward is the possibility that we use a new technology to build what is called a Muon Collider. That would be an entirely different machine that we haven't yet the technology to build, but we think we could have it in 20 years. And muons, we can accelerate them and collide them exactly because they travel close to the speed of light. Because a muon decays in 2 millionths of a second. So if you take a muon and after 2 microseconds is gone. And how can you actually take it, produce it, make it turn in a big machine, and then bring it to collide with another muon? You can do it because when you accelerate it too close to the speed of light, it lives much, much longer than those 2 microseconds. In fact, its time of duration of life is expanded by exactly the factor of energy that you have given to it. So that is one other use that we make of this concept that David was talking about.
And just to clarify, in the standard model, muons are a kind of heavier version of an electron.
That's right.
Right. That rather than having that rather than being stable, existing forever, as far as we know, decay more rapidly, as you said, and that is why we need to make them go at a very high speed if we want to be able to make them collide usefully.
Yeah, so, and muons don't exist in ordinary matter, but they're created, for instance, by proton hitting the upper atmosphere, and they rain down as secondary products of the decay of the particles produced in these collisions, so that you are constantly being traversed, your body is being traversed by tens of muons every second. You don't realize it, of course, because they leave a very little amount of energy in your body, but they are with us.
And that has been always a nice way to illustrate time dilation, because if at high speeds, from the point of view or the frame of reference of the particle, time didn't slow down, then the muons would decay before reaching the surface of Earth. But instead, they exist, and that has been a good way of illustrating that. Now, my provocative question is that during the Manhattan Project in Los Alamos, Oppenheimer and colleagues ran a calculation where they were pretty sure that by exploding the atomic bomb, they would not start a chain reaction, igniting and consuming the atmosphere, right? And then they crossed their fingers and they exploded the atomic bomb, and it turns out they were right. The atmosphere did not ignite all over the planet, killing everybody. A similar kind of calculation, I suppose, was done to exclude, for example, that the LHC could create some negative effect, such as creating black holes through the collisions, and that hasn't happened, at least not yet, or rather, the black holes that are being created, if there are any, are so small that their rate of evaporation is very, very large, and they just go out in a puff.
And it would be an incredible scientific discovery. In fact, although it has not a lot of credit, there was a theory of which implied that quantum gravity effect could actually appear at the TeV scale, which is the scale of energy probed by the proton collisions of the LHC. We haven't found them. We continue to search for them. It is true that when you create a microscopic black hole, as it would happen in these particular circumstances, which are, however, disproven, would evaporate. It would not be able to call in new matter and become larger and eventually devour everything around it. But black holes are pretty much a real thing, and we have to deal with it. And in fact, we are incredibly happy that not only do they exist, but that they can be used to probe the universe and to look at the universe with different eyes. This is something different and is fascinating.
And for you as an experimental physicist, it must have been exhilarating to see the success of LIGO, which is similarly to the success of LHC in discovering Higgs boson, has been able to observe gravitational waves many years after these have been theoretically predicted. And so what did you think? Was that something that, if you had a bet outside of your specialty, you would have bet that it would happen so fast, or you would have said, "Oh, we will need another 100 years"?
I'll be frank. I was surprised because first of all, the frequency of this kind of effects that we can actually probe with these large gravitational antennas was not predicted. And so it was a shot in the dark. You could investigate a certain region of frequency, but the good things might be happening somewhere else. And so it was anybody's guess. Also, it was a search for many different places. And you know that if you have a small probability of finding something, but you look into many different boxes, you are likely to find a spurious effect somewhere. So when the first hint of discovery of gravitational waves came about, I was very skeptical, because I said, well, what is the trials factor of this new discovery? I mean, how many boxes have they looked into? How many different frequency bandwidths? But it is a true effect. And the incredible thing about this is that these instruments are really stretching in a mind-bogglingly way our technology, because we are shining light back and forth gazillions of times through mirrors that are kept in a situation that allows them to be so precisely constructed and held in position that by interferometry you can measure distance scales that are a tiny fraction of a proton's diameter. And so
and what is very smart about the whole setup is that it is using the universe itself to study the universe in experiments that are kind of a natural configuration for something that would be impossible for us to do. In this case, we are talking about the merger of two neutron stars, or of two black holes, or a black hole and a neutron star. cosmic events that, as you said, we didn't know how frequent they are. Now it looks like they are more frequent than we expected.
Yeah.
And
it's unbelievable that you can actually pinpoint the region of sky that this thing is happening. It happened millions of years ago, of course, but you see the waves coming because you have instruments that are oriented different ways. You can pinpoint the direction. And then we have many other ways of looking at the sky, and we can correlate them together. So we can find an optical counterpart of this merger of black holes. For instance, we can look for photons, or we can look for neutrinos or cosmic rays. So this is incredibly exciting because it's not opening a new page of a book of fundamental physics, is taking another volume and
yes.
fresh.
One of the unique properties of gravity, which Emiliano will again hate, is that contrary to other forces, there is no such a thing as anti-gravity. It cannot be shielded. And as a consequence, gravitational force goes everywhere. Yes, it becomes less and less powerful. That is why when something is so far, we need a gravitational event as strong as the merger of two black holes in order to feel the effect. But it also means that there can be every possible optical shield that stops us from seeing something, including the glowing of the initial fog out of the Big Bang when matter was dense enough so that the universe itself was not transparent. But with this kind of new volume of probing the universe and astronomy that is based on gravitational waves, we are going to be able to go beyond that to look at the Big Bang and many other phenomena that are invisible otherwise.
Yeah, so I think of it this way: there are four fundamental forces in nature. And until 100 years ago, basically, we were only using for fundamental research electromagnetism. Because, okay, we understood gravity, it allowed us to explain the motion of planets, but we couldn't use it for experimentation. And then we started designing an accelerator, and we were able to probe another force, which is the weak force. And then we started probing the strong force. Actually, the strong force and the weak force came about a little bit mixed together, so it took us a little while to figure that out. But we had three forces that elementary particles are playing by those rules. And this fourth one, we never considered it because it was totally beyond our power to use for experimentation. And now we have it. Now we have four different ways to look at the cosmos. Okay, strong force is confined, but still we can see effects. So yeah, I think this is an incredible turnaround, and I was really surprised. And now the wealth of data that these instruments are giving is really, really exciting.
So the special theory of relativity is more than 100 years old. Quantum mechanics is almost 100 years old.
Right.
And both of them are finding applications in our daily lives. Yeah. The first, for example, is, or actually both of them are present in every time you get in a car and you use your phone to set up the map to navigate wherever you want to go. Because we use quantum effects to create the precise atomic clocks that are needed in the satellites that are in orbit. And then we use subtle corrections due to special relativity in order to make sure that the tuning of the system it works, and your phone looks at the various satellites, as many as it can see. That is why when you're in New York or in other places with a lot of skyscrapers, your GPS goes crazy because it cannot see enough of the satellites, and calculates the differences between various signals that the satellites send. Yep. So it took some time, but both quantum mechanics and relativity are now in the daily lives of people without them realizing. And so it is not going to be you, because it is not your job, but future generations of engineers are going to use linear or circular accelerators, are going to use gravitational interferometers.
Yeah, these things are ways to interact with our daily lives.
But and some of it is already happening. For example, the reduction in scale of accelerators is now overcoming some limitations in important isotopes for cancer treatments, and a lot of newer generation or very precise computer tomography is based on instrumentation that wouldn't have been available without these advances.
Yeah, I'll tell you two things. One of them is that these new hadron therapy machines well, they are not new, but they are becoming more and more available to treat cancers that are otherwise not curable and not operable, by going inside you and burning exactly the tumor cells without affecting the rest of the environment. This is a development that strongly relies on detection technology, fast data acquisition, and pencil beams of particles. And this is actually one of the applications that I want to develop in this project that I told you about. And there will be also a field test of a new device that we are going to optimize. But another of such applications that's also in my project concerns something that many people don't even know that this exists. But we talked about muons that rain up from above, and muons can be used for tomography. What it means is that you can use the fact that a muon traverses large amounts of matter to actually create radiographies by detecting muons upstream and downstream, or only downstream with certain software methods. By this means, people have looked inside the pyramids, they have looked inside volcanoes, and now we are developing an application that will detect smuggled material inside containers. So you know that one application is that people try to smuggle radioactive substances mixed with scrap metal that goes to the foundry and then creates a mess. Because, you know, if you have radioactive material waste, it's incredibly expensive to deal with it. But if you smuggle it and send it to a foundry, you're done, right? Or explosive or drugs that have a lower atomic number, so they are even harder to detect by these radiography means. So you can use the muons, because the muons provide a natural accelerator. They pass by, and you can detect the voids and the structure of matter inside containers this way. So this is another application that's very interesting, I think.
All right. And these funding efforts are a necessary and important part of a physicist's life, to be able to illustrate your ideas, convince other people that they are worthy of support, answering any objections without getting mad.
Yeah, no, but it's a competitive environment, and it is good that it is this way, because resources are limited, and so the money goes to the really worthy projects. Of course, you have to sell yourself well and sell your project well and your idea well, but that's part of the game, and everybody abides to it because it's better to get funded and have a chance of getting funded than not having any. But even if I didn't get any funding, I can live a comfortable life because I'm part of this huge experiment, and I can spend all my life, many lives actually, analyzing this incredible amount of data that the LHC has been producing for us.
And that is a wonderful statement that others would label negatively. Oh, it's a privilege, and that you don't deserve it. But the problem is the opposite. Everybody should have the chance of doing what you do, doing things that you love to do, and doing it for not one lifetime, but for many lifetimes. And that is what we have to strive for. And that is, I believe, what robotics and AI and everything that so often is labeled, oh my God, we won't have jobs anymore because all the jobs are going to be taken by these machines. Let them take those jobs. We want to go back to the peripatetic school of Plato and Aristoteles, when rather than with human slaves, with metallic slaves that do the work, so that we can philosophize and we can design as crazy machines as we can. Martin is saying that general relativity is used in GPS as well in order to correct for the diminishing strength of gravity. I suspect it maybe in the later generations of more precise instruments that reduced from several meters to now a few centimeters, the precision of GPS, but I am not sure. It is funny, I spoke to one of the original patent holders, who is now in his 80s, for GPS systems, and he doesn't believe in special relativity.
Okay, well,
he has
anyway.
He has some alternative theory, and I didn't have the time or the patience to listen to him, and I'm sorry to admit that. But that was quite amusing, because of course he's the father of the whole system, and the system uses the theory that he doesn't believe in. So Emiliano is asking another important question: is the cat alive or dead in the box? And
do you want me to take it? I don't know.
Why don't you have a shot at it, and then I will have my answer too.
So this has to do with what reality is, and ultimately it has to do with our definition of what reality is. Because you could take a perfectly well standing point, is to say the cat is definitely either dead or alive, and we don't know because the box is closed until we open the box, but the cat is in a definite state. This is natural non-quantum mechanics answer. In quantum mechanics, we live in a superposition of states until a measurement collapses the wave functions and selects one of the two possible worlds. In fact, I believe that it's perfectly legal to consider the fact that we live in a superposition of possible worlds, and the theory that has been developed for this is called the many worlds view of quantum mechanics. And so the cat is in a superposition of states. There are universes in which the cat is alive and universes in which the cat is dead. all possibilities that are not violating laws of physics coexist at the same time with different probabilities. And this is all enshrined in a thing that is called the wave function of the universe, that nobody can write, but it contains the various probabilities of different things occurring. So the cat is both dead and alive, and the question is, what is your reality? That is my answer.
Quantum mechanics bothered and still bothers a lot of people, including famously Einstein. And the reason is because it is so far from what our intuitive sense of reality tells us that we see it as it shouldn't exist. And for a long time, a lot of physicists tried to find a way to prove that these kinds of crazy things that quantum mechanics implied were only a consequence of our insufficient understanding, and that introducing further components, the craziness would disappear. And it has been unfortunately proven that it is not the case, that the hidden variables that they were looking for are not there, and that the phenomena that quantum mechanics represents through the experiments are fundamental, in the sense that if we keep going and if we understand more and more, we will be able to describe things that today we can't describe. We will be able to build machines that are incredible and magical if observed from today's understanding of the world. But those experiments, those machines, those results will be based on this craziness, will not be based after eliminating the craziness. It is how the universe is.
It's with us.
Huh? I didn't catch that.
I said it's with us.
Yeah, it is with us. It is gonna stay with us, and I think that a wonderful use for AI, and hopefully humane, in the sense that after the fact we will ask AI about it, and the AI will respond, "It's fine, don't worry," is to grow an intellect that is natively familiar with the quantum world, so that what we are saying is crazy, for that intellect is natural, and our intuition will not be able to grasp, but its intuition will be able to leap, because it will perceive the world at those quantum levels. And biological humans will never be able to be born and to be bred and brought up like that, and we would never expose a human child, to that kind of experiment.
Will we crossbreed?
Well, that is the next step, obviously, regardless of what kind of extension of our abilities we want to achieve, and at what depth we want to intimately accept that kind of extension. Some of us, for example, you, would welcome the ability to redesign your cognitive functions so that you could acquire this ability to intuitively reason about quantum phenomena.
Yeah, certainly. But the brain, our brain is a plastic thing, and we can redesign and reconfigure it every day. And I do it daily because I play the piano and I try to reconfigure parts of my brain in order to be able to move my fingers faster. So we are doing this even if we don't think about it.
Oh yeah, absolutely. We are. Even though, because that would be Emiliano's next question, no, we are not using just 10% of our brain's abilities. And the reason is relatively simple. We are already born at the limits of the volume that is possible to be grown inside the womb. And if we had 10 times as much as we needed, then evolution wouldn't expose us to the incredibly high probability of dying while being born.
So are you blaming women's vaginas that we aren't more intelligent than we could?
Well, being grown inside an artificial womb will mean that the current limitation doesn't apply anymore. Right. So we'll see whether that will be taken advantage of. My guess is that there will be better and faster ways to improve cognitive function, and biological evolution is not gonna used much, because it would take millions of years to take advantage of it.
I know we are both for
patient
technologies, not for incremental ones.
Yeah. So Emiliano is saying Neuralink. Absolutely, Neuralink is going to be one of those, and interfacing with AIs is going to be done through those kinds of brain implants. But of course, we will have to be careful. And if you want to learn more about this topic, you can go to my Patreon page, because I have a weekly episode called The Context. And this week's episode is about being an ambivert, not an introvert and not an extrovert, but in a dynamic situation between the two. And I conclude that episode saying that it doesn't matter what is your cognitive limit, AIs are going to also have to set a dynamic balance between being introverts and extroverts, because they will want to absorb as much as they can. So Neuralink is going to help, but it is not going to be the end all to all our problems. We will just increase the reach and immediately hit new limits. You know, just like when you create a highway and there are too many cars, and then people say, oh, we just have to add another lane and everything will be fine. No, with a new lane on the highway, you have more cars filling it up immediately. And in LA, there are now highways with 8 lanes, and all of them are completely full all the time anyway. So the same is going to be with our cognitive functions. And it's not that it will not be good; it will be good, but we will have similar challenges as we have today. So Tommaso, thank you very much for being with us today for an hour and a half. We could go for many more hours to discuss about physics and the cosmology and the particle physics and philosophy, because a lot of these topics are deeply philosophical as well. So maybe if you are available in the future, we will do some more of this.
We can do more of that for sure. And of course, we are both distributing ideas and things with our blogs and various sources anyways. So, and we are easy to reach.
Thank you. And thank you, Emiliano, for for all your wonderful questions, as well as Esther, who has been also chiming in and also answering some of the questions that Emiliano was asking, and I didn't pick for being answered live. Our viewers are collaborating and helping each other too, so that is wonderful. So thank you, Tommaso. Thank you, everybody, for being with us today on Searching for the Question Live. I already mentioned my Patreon page, where you are welcome to become a fan, a supporter, a sponsor, or a benefactor at the different levels that are available. If you are appreciating the conversations that I am having with our guests. If you speak Italian, se parlate italiano, subscribe to my Italian channel by going to davidorban.com/YouTube Italiano, and sign up to my newsletter to be alerted about what is going on. But come to the Discord server on davidorban.com/Discord. We continue the conversations. And if you are like our live commenters, Emiliano and Esther, you will enjoy continuing to probe the themes that come up on the show. You can actually also steer the show in directions by suggesting who should be a guest, as well as voting on guests that are suggested by others. So all of this will, I'm sure, shape Searching for the Question Live in interesting directions for many episodes to come. Thank you, and see you soon.